Hi everybody. Wow, I've never had something like that happen before on YouTube. Usually it's a technical issue. Um on So to describe what I do, I think the best way to do is for me to do this. So let me see if I can capture this so you could see what I do. Actually, I can't. So what I'm going to have to do is I'm going to have to put this over here. And then I will do, let's see here. Display capture. And I want monitor 1. Yeah, that's what I want. So this is what my screen looks like, which is going to look really stupid. I'm going to make this big so that it like zooms into the distance forever. Ooh. This is the program that I use, and so what I do here is I click through these buttons down here to change scenes. So there's the title that you can see and the lecture. Sometimes when I hit this button to start, nothing works. Everything just breaks and collapses and it all falls apart. And then I have to figure out why, and that's buried in the settings, or it's buried on YouTube, or whatever. Maybe my internet is down for the day. So we'll hide that. We'll never look at that again. But usually that's the issue. It's usually OBS. Today the issue is YouTube. I cannot log in or out of any account from YouTube. When I click on the little picture in the top right corner, I just get a little spinning wheel. And I don't know why that is, and it doesn't matter what account I'm on. But thankfully, Google will let me log in and out from email. So I just logged out of all my emails, and then I logged back into Everett CC email, and that worked. And then I was able to get to YouTube. So I was like, okay, great. But yeah, I've had the whole gamut of why things won't work. For getting this started. So again, if you have yeah, no, don't use Streamlabs. I have a friend who upgraded Streamlabs this week, and no matter what he does, it will not stream at all. And it's purely a Streamlabs issue. I use OBS because it's simpler. Like, that's the whole point. Are you gonna DDoS me? Please don't. I have a job to do. So again, if you weren't reading the chat and you just got here and it scrolled off by now, in the event of a technical mishap, the first thing I do is message you guys in Discord. I don't post announcements for these things because, one, the setup that we have on Canvas is stupid for a 50-person class. I have to type in an announcement, set a future time, synchronize the websites, and then it will send it out at that future time. If I send it, it will post it to the blueprint, and it won't actually send you a notification. So my first line of contact is Discord. So if you're sitting there like, it's 12:19 and the stream's not up, what the hell's going on? Check the Discord, and that will you'll probably see me like panic messages from me, like, why isn't it working? Okay, but we're live now. I mean, we've spent 10 minutes just getting all that set up, but that's okay. Things to note. So quiz number 1's due Thursday. Make sure you get that in by the deadline. Remember that for deadlines for quizzes, the date that's listed on the calendar, which will also appear, are people still getting the feed? Oh, I dropped some frames. It should pick back up. Hopefully it's working. Otherwise you can refresh the window. Sorry, that's Comcast's fault. For deadlines for quizzes, the date listed on my screen at the bottom here. So where's my pen here? Let me try and indicate that a little bit better. I can't actually see the thing. There we go. So that would be right. So I'm trying to look at another monitor while doing this. So right here at the very bottom, down below this arrow, that due date and the date on your Canvas calendar are the soft deadlines. So if you don't finish your quiz by the end of that day, there is a 24-hour period after that. So the 15th is when it closes, and you'll get a last call email at 6 p.m. that day. Any other questions? Let me know. I realize we're all over the place today. All right, when we left off last time, I talked about the, let's see here, what did I do? We were talking about metric. We said that metric was stupid. And then I skipped ahead and I showed you this metric or I talked about Imperial being stupid. And then we talked about this table of numbers that is going to be important. Try and have this handy. Because typing this into Google every time you need to change from millimeters to meters or kilometers to nanometers or whatever is super obnoxious. Is far faster, believe it or not, to do the calculation. Because typing in all those zeros in Google or typing in all those decimals is frustrating. So have this slide handy for the purposes of this class. If you have to like type out a little like printout or something and have it like taped to your monitor, absolutely worth it. This is the one instance where having like a table is just faster than Google. All right, so let's go back. Let's talk about what we're going to measure in this class. We're going to measure 5 different dimensional units. Not 5 dimensional units, but there are different units that have dimensions to them. So the first unit that we're going to talk about is length. Length is a distance between any 2 points of your choosing. And the default unit that we're going to use is the meter. We're going to take the meter and we're going to adjust it either up or down for larger or smaller distances. Atoms are tiny, so we're going to use small distances for atom stuff. But if we're talking about like interplanetary things, then we obviously meters is too small. So we would use like kilometers or megameters or whatever. Volume is going to be the 3-dimensional space that something takes up. All volume in this class is going to use the base unit of liters. And then we'll modify that as appropriate. So milliliters is more appropriate for chemistry stuff when we're like measuring out water and things like that. The next one's mass. Mass is just simply how much stuff you have. So stuff being matter. We're going to use grams as the default unit. Grams are actually pretty small, so that's helpful. Excuse me, that's helpful for us. Time is how long it takes between 2 events. We're going to measure that in seconds. And then finally, there's the new unit, which we're going to talk about in Chapter 6. This is how much you have. We're going to call that unit for now the mole. Sorry, I had to keep muting here because I keep coughing. I don't have a cold or anything. I just have congestion from like, I don't know, it's April, right? I might be like mildly allergic to the sun. Good thing I live in Seattle, right? All right. Now, these are all of our base units. And what we can do is if I write down any of these units, for example, I'm going to just write down the liter. I can put in front of it a prefix, and those prefixes are what we saw on the other page. Those were things like this. And I can put in any of those prefixes in front of my base unit. So this is my prefix. And this is my base unit. And what the prefix does is it modifies this value to be what we want. So, for example, a centiliter is much smaller than a liter. So we would measure smaller units than a liter. If I replace the centi with some other prefix, such as, say, like a megaliter. Sorry, I'm trying to change to the pen here. Now I'd be measuring things that are much, much, much larger than a liter. So it's going to depend on how much stuff you need to measure to use the appropriate liter. Most of these problems, I'm going to give you a unit in context, and you're going to have to solve for it that way. And so again, here are those units, as well as their values. Now, how do we read this chart? This is a very important skill, because intuitively, these numbers are linked to these symbols that you have here. So these numbers on the right and these symbols right next to them. However, we want to make these into a sort of equation that makes sense for us. So I'm going to set this on the screen here, and then I'm just going to scroll this up a lot so that we're not drawing on it. And so here's what we're going to do. In order for something to be equal, I have to have two things on both sides of the equal sign that are the same value. So this is true, but this would not be, right? I need to have the same thing on both sides of the equal sign. So the way that we're going to do this is because those symbols and those numbers equal the same thing, we're going to put one of each on each side of the equal sign. So for example, if I pick C, I would put 10 to the minus 2 on the other side. And then what I do is I go put in the base unit. So we'll put meter, meter. And there you go. There's your equality. So put one of each of those on opposite sides of the equality. And then you can go and fill in your base unit. So one of each on opposite sides of the equal, not te equal. And if you do it this way, you'll always get the correct conversion. It is very easy to accidentally flip-flop these numbers and the symbols, or put the number and the symbol on the same sides. So do it this way. Put one of each from this table on opposite sides of the equal, and then just fill in your unit and you'll be safe. All right. So now that we know how to do that, we're going to take that information, we're going to come back to it and do some math with it, and that's going to be down here. We're going to do that in this section down here. The next thing that we're going to do is we're going to learn how to do basic math in science. And believe it or not, you and everybody in this class have been taught how to do addition, subtraction, multiplication, and division the wrong way. At least from a science perspective. It's not that adding is difficult. Like, you can punch numbers in the calculator, but the number of digits that you write down for your answer depends on what goes in it. And that's going to be in a very important concept that we cover in this section called significant figures. So this is the part of the class that everybody hates because we take something so basic and then change it on its head. But it is very important that we do this in science because, well, we'll talk about it once we get to that reason. All right. When you are measuring something like, say, your weight, if you stand on the scale and it says 184.4 pounds, do you weigh 184.4 like it says, or do you weigh this? With just infinite number of zeros after it. Are all the digits after that 40? Do you think it's likely that you'd land on exactly 0, 0, 0, 0, 0, 0, 0, 0, 0 forever? Almost certainly not, right? You probably weigh some number between those two. 184.4, 180,963. It'd be something like that, right? It'd just be some random set of numbers. But what your scale does is your scale says this. This is all I know. Past this, it's just a random set of numbers. I'm not precise enough to measure that. And so any numbers after the cutoff that it shows are essentially random. Now, they're not entirely random, because if the next digit here was 5 or higher, this would round up, right? But what we do know is that this is going to be some number. And heck, this last digit could be a 3, but it could be 3, and then the next mystery digit is 8, which would round up to 4. So it is essentially random what comes after the numbers that your scale prints out for you. So when you weigh yourself, you are getting this. A mess. That's what we're getting. We're getting a mess. Sorry, if I tap the pen at the same time that I accidentally push this button on the pen, which is conveniently right next to my thumb, that happens on the screen. When we weigh ourselves, we get something called this. We get what's called an inexact number. Any measurement with a tool will produce an inexact number because it can only tell you so many numbers, right? If you're using a ruler to measure your height, and your height is 61 inches, you could maybe guess the next number. You could say, like, oh, I fall between 61 and 62, so I'm like 61 and a half. But can you guess the next digit after that? Are you 61.54? 61.58? At some point, you run out of lines, right? And you can't tell what the next digit actually is, so it could be random. That's going to be inexact. And this is going to be true for any time we measure using a tool. When you measure stuff, it is virtually impossible to get an exact number. There is only one circumstance in which you can get an exact number. And that is when you count it. So if I go to YouTube and I click on this button here that says how many people are watching the stream, and it says 19. So if there are 19 people watching, it's not going to be something like this, right? That doesn't make sense. You can't have fractional people. Everybody counts as one. So we would say that a counted number is exact. Because when we count by numbers, there is no error associated with it. At least until YouTube updates. Now there's 21 people watching. Probably because connection issues or whatever. The other form of an exact number is something that we just say is true. So for example, in this conversion here, there are 1,000 milligrams in a gram. That's true because we said so. Like, nature doesn't know what a gram is. It doesn't know what a milligram is. Those things don't exist in nature. Nature doesn't have a numeric or counting system. Therefore, as a society, or civilization, I should say, we just elected to write down, okay, this is going to be universally true. 1 gram equals 1,000 milligrams. That is exactly true. So anything you define and anything you count are going to be exact. Now be careful. Not all equalities that are written are definitions. Anything that's a definition, I will explicitly tell you. Anything that is a conversion is basically me measuring against a ruler. What if an object weighs an exact amount like a component on the space shuttle? So even that is not exact. And the reason for that is that if I want something to weigh exactly 200.00 pounds, all I have to do is get, so if this is the number that I want exactly 200 pounds. Any number between this range will satisfy that requirement because the cutoff is the second decimal. So if I'm rounding to that decimal, both of those numbers round to 200, and therefore everything between them would too. So even when they say, I need an exact mass on this, it's not truly exact because as you get further and further and further past what you were able to measure using whatever device, you can't determine those numbers. Pi is an exact, for example. Very good, yeah. Because you never know what the next digit is, right? I mean, you could calculate it, but we don't know what it is all the way down to its last digit, which theoretically doesn't exist. Now, the more digits you can write, the more precise you are. So a space shuttle component would be very precise, i.e. there would be a lot more decimal points. However, it would never be exact because you can never know the next digit past the end of that precision. So let's look at examples of inexact numbers and learn how to calculate them, because it's going to depend on the tool that's being used. If you have a balance or a scale, you can trust the numbers that it prints at you. Those will be known numbers, and then you can just assume everything past it is unknown. Otherwise, it would show it to you, right? But what about something like a ruler? If I gave you a ruler and I said, okay, this ruler goes all the way to 0, and our object is flush with the end of the ruler, so it's not hanging over or whatever, it starts at 0, and this is its length, what would be the appropriate number to write down? So what I want you to do is, in the chat here, I'm going to just chug a little bit of water here while you do this. I want you to tell me what you think the length of this object is, and I'll even zoom it in for you. So we'll just do this. So I want you to tell me what this length object is, and also write the units, because the units are shown. So make sure that you do that, okay? So do that in the chat. I'm going to give you like 2 minutes to do it, and I'll be right back. All right, I'm back. I got more water. Trying to clear out my sinuses from, like, I don't know, pollen or cat dander or something like that. It's probably the cats. I can't wait until it's warm enough to just have all the windows open all the time. But if you're looking over the answers in the chat, you'll notice that not everybody wrote the same thing, right? How do you know how many digits that you can write down? And so what we're going to do is we're going to go over here. And I'm going to give you the rules for how to measure anything. Oops, I got to clear that off the screen. There we go. If I don't clear the little, like, selection tool, then it doesn't always let me write. There we go. Okay. So this is going to be based on the tool markings that are present on the tool that you have. Okay. So step 1, what you're going to do is you're going to identify the 2 marks the object lands between. And then what you'll do with that is write the value of the smaller mark. All right, so that's step 1. And then step 2 is to guess one more digit based on what you visually see is in front of you. So I'm going to leave this on the screen here, and we're going to go back over to this thing, and hopefully you can see my cursor now. We're going to follow these rules. So the first thing I'm going to do... Oh, let me zoom this in again. Oh, I can't draw when it's zoomed in, so never mind. Where'd my cursor go? There it is. We're going to identify the 2 marks that this object falls between. And so we would all agree that it's these 2. So step 1 says identify the 2 marks, so we did that. we're going to write the value of the smaller mark. So what is this mark's value? It would be this, 11.6 centimeters. So that's step one. I've written the value of the smaller mark that has bounded this object. And then step two is to guess one more digit based on what you see. So I'm going to zoom in. And to me personally on my monitor, it looks like the edge of this line is just short of the midpoint. Now, your eyes may vary. You might say, oh, it's exactly in the middle. And you know what? That's okay, because what are we doing? We are, and I have to switch back over here, we are guessing the next digit. Which means that you might have written this is your answer. Or maybe you wrote this is your answer. Or maybe even you aren't sure and you wrote this as your answer. But what you would not have written is you would not have written this, right? So even though you're guessing, you know that some numbers are out of bounds. Like 9 would be way over here, closer to this end, and it's not. So we know it's not this, and we know it's not going to be 8 or 7 or 0 or 1. Like, we can exclude some digits, right? So we are sort of honing in on what it is, but there's going to be some error associated with it because we are guessing the next digit. So if you guess that it was any of these, you have written the correct measurement. So that's what we're going to do for tools. Follow these two rules. 1, identify the marks and write the smaller mark as its value. Write that down. 2, guess the next one digit based on what you can tell. Don't write any more digits, because what would we write after it? At that point, we're essentially guessing randomly, right? Because we don't have enough lines to help guide us. I should go back to this screen before I continue. There we go. All right. So my little walkthrough is going to do the same thing that we did just there. I wrote down 11.64 because that's what I thought it was when I made this slide. Let's do another example here based on marks. So I'm going to give you rulers A and B here. And I'm going to just zoom in. I'm going to put ruler A on the board. What I want you to do is, based on this ruler, you'll notice the marks are different. Tell me the length of this wooden dowel, we'll call it. So type your answer in the chat. Tell me what your answer is. All right, we got a bunch of numbers. Let's follow the rules and we'll get the answer here. Oh, there's my cursor. Okay. I have a little thing that popped up and I was confused. Oh, I'm using the wrong end of the tool. That's why. All right. Identify the two marks that this falls between. We're going to write the first digit right here, which is 4. And that's all I get from the marks. And then I would estimate that this is probably almost in the middle. So I'm going to just write that, and then I write the unit. So that's what I'd write for ruler A. And it looks like everybody got that. Very good. If you're off by 1 in either direction, your answer is still okay. So if you wrote down 4.4 instead, these are okay as well. Because remember, you're guessing, and everybody has different perception, right? My vision is actually particularly poor. So if you have better vision than me, which is not hard to do, you might get a different number than me. But we would agree that we would generally get on the same ballpark. All right, here's ruler B. I want you to write down a measurement for ruler B based on what you see here. So same thing, type your answer in the chat for ruler B. All right, now that we got some guesses coming in, let's do the same thing. I got to zoom out in order to write on this, unfortunately. So my object falls between these two marks, the smaller of which is 4.5. Then I would guess the next digit, which I'm going to zoom in again to try and identify. And to me, this looks like it's slightly past midway. So I would write something like this. And honestly, since I'm writing the answer key, as long as you're within 2 or 3 of the last digit, you're fine. All right. Now, when I wrote the slide, I apparently went in and measured with I don't know, a really small pixel or something, and I got this. I went into Photoshop and measured it with the ruler tool. But even though I got a different number for my result up here, both of these are acceptable, as are any number that I saw in the chat. Oh, I didn't hit mute, I'm sorry. Now, the reason that we got to write that extra digit is because our tool had more marks on it. So the number of digits you get to write down is entirely contingent upon how many marks are present on your tool. All right. When you are making a measurement and you generate a number, the more digits you write down, the more precise your tool must have been. So now I'm looking at the number, and from the number, I have to envision the tool that was used to make it. And so you would say, well, if I can get 4 digits out of this, that must mean that tool is fairly precise. Each of the digits I write down is what's called a significant figure. So significant figures are any digits that you know for sure. So remember, we know these for sure. And then this last digit is our estimated guess. The last digit will always be the estimated digit. So what does that mean your tool has marks to? Your tool's marks go to the second to last digit. That is a sig fig. Now, we're going to get into some situations where this gets weird if we're not doing decimals. And you're going to see that in just a second. And that's kind of where all of this starts to break apart, is people get confused on the significant figures rules for turning a number back into what tool was what tool generated that number. Because we've worked with really precise stuff. What happens if we work with stuff that's imprecise? And we're going to get to that in a second. Now, if you have a better tool, you're going to get more digits. So if I was able to measure something like that dowel we had, and this is the number I wrote down for it, that's a lot more digits. That means that we're not using a ruler to do that. We're not even using machine calipers to do that. We're using laser interferometry or something like that to get something that is that precise. So the better the tool is, the more precise it is. Six is this. So all of the digits are sig figs. So the number of sig figs would be the number of digits that were written down. Let me clear this out here. So in this case, I wrote 1, 2, 3, 4 digits down. So I have 4 sig figs. Here I was able to write 9 down. 5, 6, 7, 8, 9. So I get 9 sig figs. All right, so we now can count the number of sig figs in... Sorry, a cat just landed on my feet. Maya, go in your bed. Maya, don't meow at me. Go in your bed. Maya. She thinks I'm paying attention to her, which I kind of am. Okay. So the more digits that you can write down, the more precise your measurement is, and the more sig figs you have. So sig figs are just the number of digits you can write down that are known. So what we need to do now is we need to understand what a number means when you just see the number. So I'm going to give you this number here, and I'm going to give you a bunch of graduated cylinders. So before I start the problem, I don't know why there is this mark here, but at the very bottom of each of these is 0. C is just the same for B, but zoomed in so that there are more digits. What I want you to tell me is which graduated cylinder, A, B, or C, should you record 540 milliliters? So type your guess in the chat, and I will pet the cat. Oh, the cat just ran away. Although she heard me say cat, so I'll let you do that. So I'll be right back. Say hi. Hi. There we go. That was Maya. Maya loves attention. She loves talking into the microphone. You might actually hear her in the background, because she just makes these little chirping noises. That's what Maya sounds like. She's very quiet. All right. Everybody said B, and that's the correct answer. So, very good. Now, why is B the correct answer? Let's follow the rules for measuring and see what we can do. So, for graduated cylinder A, you'll notice that there are marks for every 1,000. And so my marks here would be 0,000 and 1,000. So for graduated cylinder A, I would say that I have 0,000 milliliters, which is weird to write it this way, but you'll see why I'm doing it in a second. So I have 0,000 milliliters. I would then guess the next digit, which I would say, well, it's right in the middle, so I'm going to guess 5. Now, if I just wrote this as my answer, and I said, oh, there are 5 milliliters in here, obviously there's more than 5 milliliters, right? Because it measures 1,000, it's half full. So what I also have to do is I have to do this. I have to put zeros in here. And we're going to find out that those zeros are actually just placeholders and not sig figs, because they're not known. But for now, I have to put these zeros in here. Because I need to adjust the magnitude of the answer to match with what I need it to be, right? So for example, if I owed you $3,996, and then I said, I'm going to round that up to $4,000, and then I'm going to say, I don't need these zeros because zeros aren't significant. They don't have value. And then I paid you this much. You'd be like, you're full of bullshit. You owe me $3,996. You're not allowed to pay me 4, right? The zeros here adjust the magnitude of our answer so that it is the appropriate order to represent what we want. So these zeros are important, but we don't know their value. Oh, boo, I erased a 0. Was the first 0 because it started with 0 on the cylinder? Yes. So I have a mark here at 0, and my object fell between these two marks that I put in red, so I have 0,000, which is why we had to do that. So for A, you should write 500 as the volume of the graduated cylinder. I didn't mean to do that. We'll just write again. Oops, that's not the pen tool. There we go. All right. For B is much more in line with what we know. So here's 500 and here's 600. I'm going to write the first mark. 500 something, right? Then I would guess the next digit. This looks like it's just slightly under halfway, so I would write this. And then same deal. I can't just report 54 milliliters because it's way higher than that, right? I need this 0 to adjust the magnitude. And then finally, for graduated cylinder C, we do the same thing, except I'm not lining up my pen stroke correctly. So I write down the first numbers that I know. So it's 540 something. And then I would guess the next digit, which I'm going to guess to be like that. I don't need any zeros for placeholders there because that number I wrote down approximates the number that I actually have very well. There are no placeholders needed. If I add another 0, it'd be 10 times too big. So you can see the more marks gives you more digits, like we said before. But the skill that we wanted to develop here was, okay, how do I work backwards from a number to envision what tool it is? And so, again, the rule is that for a number written like this must be our known number, this must be our estimated number, and then this must be a placeholder. So placeholders are a thing that exist. And we're going to have to concern ourselves with those zeros too. Now in blue, I've written the number of significant figures. The zeros that are shown here aren't actually known, because I don't actually know if this first one is 490, 500, or 510. I don't have the lines to tell that. All I can tell you is that it's roughly 500. So the zeros that we have to add, these that we're forced to add in order to make the magnitude match up, these are not significant figures. And we're going to see that in just a second. All right. When you write down a digit, and the digit is not 0, any number that is non-zero is always significant because you know it, so you're writing it down. 0 may be written down as a placeholder like we showed in that case, but sometimes it's known. And we're going to look at cases where it is a sig fig and where it's not. So let's look at case number 1. If you have a 0 and it is used as a placeholder, it is not a significant figure. Now, how do you know if a number is a placeholder? Here's what you do. If you take your zeros and you cover them up, does the magnitude of the number change? In other words, before and after me highlighting those zeros over, was this number this value? And your answer to this should immediately be, well, no. 125 is not the same as 1,250,000. So these zeros were necessary because 125 was too small for what I measured. I know the digits in what I measured are 125, but now I need to make it the right magnitude. And so we tack those zeros in there. So anytime you do this, these placeholder zeros are not sig figs, which is why I have them written in red. The blue digits are significant because they are known. In respect to the decimal point, so the decimal point has nothing to do with this just yet, but we will consider a decimal point in a second. Oh, I see what you mean. Yeah, with respect to the decimal point. So the decimal point follows the ones place. So you would need to add enough zeros so that you get the right magnitude relative to wherever the ones place would be. Because that's how we numbers, right? When I write a number, I assume the last digit written is the ones place. Like, I would not write this number and say, this is actually 3,820. Like, that doesn't make any sense, right? So we need that 0 to indicate that. And that 0 would be a placeholder. All right, here's another example. We can do the same thing with a highlighter. I'm going to go like this. And so I have a number here. I have 4,386. But when we measured, that number is far, far, far too big. I know the digits are 4386, but now I need to adjust the magnitude so it makes sense. If I'm measuring something really tiny, I need to put a bunch of zeros in front of it, right? These zeros are placeholders. They are purely intended to just force the magnitude of the number to be where we need it to be. All right, so with that in mind, we're going to take a short break because we're at our break time. And let me get the timer on here. And let's play some really haunting music for Chrono Trigger. Like, this song stuck with me as a kid, and I hope you enjoy it. There we go. I'm going to wind this down here. Welcome back. Hope you were able to fill your water, step outside. It's actually... No, it's not sunny. Never mind. I thought it was sunny earlier. Now it's overcast. At least up here in Everett. I live in South Everett, so... Your mileage may vary. But we left off right before the break talking about placeholders. Remember, if you aren't sure if something is a placeholder or not, use the little trick where you just cover up the other digits. And if the magnitude changes and no longer is anything close to what you were working with, then those zeros must have been placeholders. Placeholder zeros are never significant. They are only written as 0 because we need them there for numbers to function how numbers work. All right. Now, what happens if you have a 0 in your measurement? If you have a 0 in there, so let's suppose that I measure, like, your height, and your height is 60.5 inches. This 0 in the middle is known, right? You aren't 67.5 inches or 62.5 inches. You're 60.5 inches, right? This 0 is known. So anytime you trap a 0 between digits, that forces it to be known, and known numbers are significant, right? So in this phone number here, this is Jenny's number, just in case you are my age or older and you recognize the song. That 0 is known. It just happens to have fallen on 0 when we were counting these digits. These zeros, on the other hand, over here, these are placeholders, because if I get rid of them, the value of the number changes. Now, that song I can't play, because I will get copyright struck. Unfortunately. All right. And so this will be true of any tool that you use. You might get zeros in your number. If you measure the volume of something and there are marks for every, like, 1 milliliter, and you measure 100.4 milliliters, those zeros are known. You don't just delete them. All right. There's one last important thing to remember about sig figs, and that is whenever you have a decimal, it makes determining sig figs very easy. Now, very, very, very importantly, if you have a decimal, you must follow the decimal rule. And so here it is. So the first step, find the decimal point. Boop, there it is. We found it. If the decimal point is present, we must use the decimal rule. All right. Once you have found the decimal point, underline any numbers that are not 0. So here we go. I've underlined those. And then anything to the right of your sig fig. So I'm going to put little check marks here. These are sig figs. Anything to the right is also a sig fig. Anything to the left was a placeholder, and you don't count it. Now, how the heck does this work? Like, why are those zeros known all of a sudden? Well, first of all, let me clear all this stuff off the screen here real quick. I'm going to erase these. And then I'm going to pull out my highlighter. Remember that we said that if you obliterate zeros and they change the magnitude of your number, they're placeholders. But if I do that here, you'll notice that the value didn't change, right? It's still 0.003835, regardless of whether the zeros are there or not. Since the value doesn't change, why would we write them? And the answer is the following. So we'll keep these rules in case we need to come back to them. I'm going to give you a much smaller number so I don't have to draw as many marks here. So I'm going to submit, let's say that you measured something and you got this as your measurement. And you're asking yourself, why is this 0 included? Well, let's draw a little scale here. So here's my scale, and then I have an object, and the object's length is right here. So let's follow the rules for measuring, because I didn't erase them, and that turns out it's immediately relevant. Identify the marks that the object lands between. Well, it landed right on this one, so I'm going to say that it's between these two, right? And I'm going to write the known digits based on the mark. Then I'm going to guess the next digit. What is the next digit? Oh, because it landed right on the line, the next digit is 0. So it's possible for you to land on a line. And thus, you know the next digit is 0. Now, could you have written a 1 here? Sure. I don't see why you couldn't write a 1. You could also have written 0.259. But I tried very hard to make it look like it landed right on that line. And if it lands on that line, you're allowed to guess 0. So, zeros that show up after sig figs, when the decimal place is present, are written there because they are known. And thus, we must count them as sig figs, okay? So, if you have a decimal and there are zeros to the right of a bunch of sig figs, they count too. And it is for this reason, because our object simply fell right on the line where our marks were. All right, now that you've seen all the rules, I want you to tell me, so here's more examples here. That you can pause the video and look at these if you want another reference. I want you to tell me how many sig figs are in each of these numbers as written. Okay, so I'm going to highlight the numbers that I'm intending for you to do for this example. That's the pen. I didn't mean to do that. I need the highlighter. There we go. So I want you to do these numbers. So this 900, 90210, the mass of this flea, and then 500 milliliters. Oops, and then I got to select the pen again. There we go. So I'm going to number these. Actually, just for clarity, we'll letter them. So A, B, C, D. And I want you to tell me for each of these entries, A through D, how many significant figures are present in the numbers that I highlighted. I'll give you a few minutes to do this, and then we'll go over the answers in just a second. All right, one more minute. We'll go over the answers here. All right, let's go over the answers here. So for this first number right here, 900, only the 9 is a known digit. These other zeros are placeholders, so 900 would have one significant figure. What's the difference between A and D? Yeah, the decimal is important. So that dot there, this is not a typo, so this dot does matter. For B, 90210, so these are all significant, including this 0, because it's stuck between them. But this 0 is a placeholder. So there would be 4 significant figures. For C, we apply the decimal rule, so these are significant figures because they're non-zero. And then everything to the right is 2. So this would have 3 sig figs. And then after D, yeah, so I highlighted this dot, right? That was intentional. So this follows the decimal rule, and so everything to the right is significant. So this is 3 sig figs. So if you notice that, excellent. So that's one of 2 things that I want to go over in this screen real quick. Let me put these all on here. Is that, oops, I clicked on the wrong thing. There is a difference between this number and this number. Now, that's super obnoxious, but is very important to realize, because the intent is if a decimal point is drawn, you must follow the decimal rule, right? So here's my 1 sig fig for this number, and then here are my 4 for this one. So if you see a decimal point, it always applies the decimal rule. The other thing that I wanted to mention is that how the heck do you get a number with a bunch of trailing zeros after it? So for example, to go back to what we were doing before, what if this was the number that I got for my measurement? And I said, okay, well, there are 5 significant figures. It's these 5. But how would you get this on a tool? And the answer is, remember that the second to last digit is where our marks are. So if our marks look like this, we could have a mark that says 0.2598, 0.2599, 0.2600, 0.2601. And then if our object falls right here, right on this line, I would write down the known digits. So those are my known ones, and then I would guess the next digit. Is there a 0 after the decimal point? Not unless it's written, so be careful. For 2000 dot, there is no 0 after the decimal point. If there was, I would have written this. And then I'd have more sig figs, right? Those are different measurements. The tool made to generate this measurement is better than the tool made to measure this one. So not only are you getting information about the value of the number that's written, you're also getting information about the tool used to measure it. In this case, with the 5 sig figs over here, I was able to measure down to individual ones. And then I could guess the next digit past that, which would be the tenths place. But for the 4 sig figs one, I was measuring by tens. And then I was able to guess the last digit as being on 0. So again, that's the important part about significant figures, is not only is it telling you a number, it's also telling you about the tool being used, because that's going to matter. In fact, it's going to matter right now when we go to the next section. Now, very important, you can see that there are 40 practice problems for this concept. Do as many as you can. I also have a worksheet. Make sure you do the worksheet problems, because you want to be able to tell how many sig figs are in a number as written. And the reason for that is because now what we're going to do is we're going to do math with these. And we're going to do math using the rules of sig figs, which means that we care about which numbers are written and which are not. And this is where everybody's brains explode. Why did 0.0870 have 3 sig figs? Because that was what I wrote down. So if I write down this number, then it is assumed that I measured with a tool that measured to this place, and I guessed the next number to be 0. I can't just add extra digits to a measurement. If I make a measurement and give it to you, you don't get to edit it. Just like if I say, okay, I'm going to charge you $84, you don't get to stick a 0 after it and say, oh, it's $840 now. Haha, sucker. You can't do that. Same thing, if I measure something and say, this is 11.0 inches, you cannot say it is actually 11.00 inches, because then you would be misstating how precise my object is. And if I needed to have something that fit 11.00 inches, let's write that down. So let's suppose that you needed something that was like this, and I gave you something that was like this. This number, again, could be any number between 10.95 to 11.04. And this would not fit into this slot, right? It'd be too big. So if anytime the number ends with 0, it is presumed to be an estimate. Yes, if the decimal rule is present. So again, remember that if it's just a placeholder, so if it's like this, it's not a guess, it's just put there. 0.08700 would have 4 sig figs, yes. Remember, just follow the decimal rule. So this number, 520, would have 2 sig figs. Sorry, I know writing on red on black is a weird contrast issue. All right, let's do some more examples, because this will help sort of cement the idea of sig figs in place here. On the board are 2 problems that I know everybody in this class can do. Everybody can add 3 numbers, and everybody can find the area of a simple geometric figure by multiplying the edge lengths together. That is trivial. Nobody has any problems doing this. What's going to gum up our works here is sig figs, and so that's what we need to consider. We're going to do example A first. We're going to do addition. And there are a set of rules for addition and subtraction. There we go. And the rules work for both of those. But then we're going to do a different example, and there are going to be rules for multiplication and division, and they are unique. So these rules will be different, so be very careful that you are not applying these rules that I'm about to teach you to the wrong operation. You're going to learn one set of rules for addition and subtraction, and you're going to learn one set of rules for multiplication and division, and they are different. So be careful. So the difference is an estimate on a measurement I take and a specific number that you provide. Yeah, so those are two different cases, remember. If you are given a tool, use the rules for measuring to provide the correct number of digits. If I give you a number, I have already followed those rules and have given you the number. So you need to work backwards from there to understand how the tool worked. The last sig fig I wrote was estimated. The second to last was where my marks were. And so you can use that information to learn about the tool. Which is why I can't just write numbers endlessly, because the tool won't allow that, right? So for instance, on this number right here, 352.8, my tool allowed me to estimate this number. That means that I had marks every one. 351, 352, 353. My object fell between 352 and 353, and it was about 8/10 of the way across. So I wrote this number. This next tool, though, down here, had marks all the way down to the hundredths place. And then this was my estimate. And that's how it's going to be for all numbers in this class. All right, let's do example A. If you were doing this math problem in like first or second grade, this is what you would do. You would just say, oh, okay, well, all these blanks are 0, and I'm just going to treat them like zeros, right? And so carry the 1, 11, 12, 15, carry the 1, carry the 1. And this is the answer that you get. And in this class, that is wrong. So this is not the correct answer. Why is that the wrong answer? Because if you type this on your calculator, that's the number it will spit out. Here is why it's wrong. Because we just said that for 352.8, that this is where our marks are, and this was our estimated digit. If our marks are every 1, what is the next digit that goes in this blank space right here? And the answer is, well, I can't tell based on the marks on my tool. This could be any number. And so could the next number, and the next number, and the next number, and the next number, and so on. So anytime there is a blank, we do not get to treat it as 0 when we're considering measurements. We treat them as question marks. And then when you do addition, what is 1 plus question mark plus question mark? It's not 1, it's question mark. Question marks aren't numbers you get to write in your answer. And so what ends up happening is when I do this math, I get this as my answer instead. And that's the number I would report. Now, doing question mark math is a little bit difficult. So here's what we're going to do to not worry about question marks showing up in our answer. What we're going to do is when we do this addition and subtraction, you're going to punch it in your calculator. And your calculator does treat these as zeros. So I'm just going to write down, oops, that's the wrong number. I'm going to write down what the calculator tells me, 535.921. And here's what we're going to do. We're going to start from the furthest to the right, and we're going to find the first position where there are no question marks. So let's start here. In the thousandths place, are there question marks? If there are, we don't get to use that digit. In the hundredths place, are there question marks? There are. We don't get to use that digit. In the tenths place, are there question marks? There are not. We may keep that digit and everything past it. There is our answer. So I have circled the first position that showed up where there is a sig fig in every spot. There are no question marks. And then I'm going to round my answer to that spot. All right. I'm going to erase what I wrote because my slides are just going to do it. There you go. So that's how we're going to do addition. Write out all your numbers vertically, lining up the decimal point, and then find all your question marks. Then start from right to left, find the first spot coming from the right, going to the left, that there are no question marks. That's where you round. All right, let's do another example here. What is 4.83 minus 0.7? So we're going to go over here. Oops, doesn't even show up on the slide. Doesn't this automatically cause less precision? Yes, and that's actually the point. The reason that this is the point is because if I have a tool that's very precise and I use a tool that is less precise and combine them together, I lose precision. So for example, this number is more precise because it goes to the hundredths place. This number is less precise. If I use tools that are less precise, my answer will likewise be less precise. So yeah, you are losing precision when doing this, and it's actually the point. Because I can't assume that the precision that my good tool had is preserved when I use a bad tool. So I'm going to do the algebra. I'm going to subtract. So 3 minus 0 is 3. 8 minus 7 is 1. 4 minus 0 is 4. Then we're going to look at each position. Is there a question mark in this spot? There is. We don't get to use this number. Is there a question mark in this spot? There is not. I round to that spot. And that's the answer I report. All right, let's do another one. So for this problem, I'm going to write down the numbers. I'm going to line up the decimal points. Notice that there is no decimal point on 7,300. Don't add one. If a number does not have a decimal point, do not put one in there. You change the intent of the measurement tool. So let's add these together. And like no surprises here, right? When we do the addition. Now, how many digits do we get to keep? Well, let's look at our digits here. So question mark, question mark, question mark, right? So I don't get to keep this. I don't get to keep this. I don't get to keep this. These are all garbo. Because the first tool obliterates that precision. Now we get to 7,300. How many significant figures does 7,300 have? Well, those zeros are placeholders, so it only has 2 sig figs. So these zeros aren't known. I don't know 73 to the ones place. I know it to the hundreds place. Which means that these are functionally question marks. And I don't get to keep these digits either. So when I add these numbers together, this is the result that I get for numbers I get to keep, which I then have to fill in placeholders so I get the correct order of magnitude. And this is where people freak out. That's a lot of rounding. Yeah, because I'm adding a number where I counted by hundreds to a number where I counted by a fraction. And if I'm counting by hundreds, I lose all that information. I don't know what those numbers are. Can you estimate the number of streets in the city? Sure, if you counted by hundreds, right? You're not going to count by one. That's way too many. So you can get numbers that have very low precision. And if you add them to high precision numbers, you get weird results like this. In fact, here's the example that everybody hates. If I add these two numbers together, what happens? Let's find out. First of all, we'll do the addition as normal. But then 3,000 only has one significant figure. So these are all question marks because they're placeholders. So I don't get to keep any of these digits. I would then round to this spot. So in this class, 3,000 plus 6 is 3,000. And if you just heard something outside, that's the sound of 50 brains exploding. Those were your classmates. I'm sorry. Why does this work? It turns out this actually makes logical sense. And I'm going to try and explain that with an analogy. You decide that significant figures are stupid and you don't want to be a chemist or a nurse or anything anymore. You're going to invest all of your money in the lottery. And it turns out that you strike it rich. You hit the Powerball and you win $656 million. Congratulations. You no longer need to take this class, or any other class, or do anything for the rest of your life. Now, you're new to this millionaire thing, so you celebrate by buying a hamburger at, I don't know, Burger King. It's the way that you know how. And you spend $7.99 on that. How much money do you have left after buying your burger? Is it $655,999,992? Or do you just say, fuck these digits, I no longer care about any of those. These are the digits I care about, right? $10,000? Who cares about that, right? I have $656 million. I could drop $100,000 and barely notice it. I have $656 million. I do not give a shit about these digits anymore. Because they're too small relative to the magnitude of the thing that you're looking at, right? If you have magnitudes that are very different, small changes in them do not affect them. Let's look at another example. I live in the city of Everett, and the population of Everett, well, actually, let's use Seattle because it's bigger. So, Seattle has a population of 700,000 or so. This weekend, a family of 10 moved in. It was an extended family. How many people live in Seattle? It's still going to be roughly 700,000, right? Because that 10 is too little to affect the magnitude. I have another joke, and you're going to immediately find this really stupid. A janitor worked at a museum, and he tells people that the bones on display are 65 million and 8 years old. And they go, wow, how do you know that they're that specifically? And he says, well, they were dug up 65 million years ago, and I've worked here 8 years. And that's what they told me when I started. And if you're immediately going, oh, ha, 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 yeah, he added the two numbers together, but that doesn't make any sense, then you understand this concept. If I give you a very rough number, we have no idea how many years ago dinosaurs lived. We know it's roughly 65 million years ago, but we don't know it to the precise year. So saying, oh, it's 65 million and 8 because he worked there for 8 years and that they told him it was 65 million when he started. Like, that doesn't make any sense, right? Oh, sorry, hold on, my phone is going off because I have to go feed cats after class. I'm watching somebody else's cats. So, when you have numbers with different magnitudes, you get weird results like this because you lose all that precision. So, that's why these numbers are doing these weird things that give us answers that we don't like. But in reality, it makes sense because the numbers are of such different orders of magnitude. So be mindful of that when you're doing addition. That yes, you are going to lose precision, and in some cases, you lose so much precision that your answer is unchanged. Let me know if you have any questions. That's addition and subtraction. So remember the rules for addition and subtraction. We'll put them back on the screen really quickly here. Look for the first place coming from the right that does not have any question marks in it. And that's where you're going to round. Addition and subtraction care about places. All right, let's go do multiplication, and then we'll be done for the day. Everyone knows how to do this problem. If you were going to write it out on paper, it would look something like this. You'll notice that I have way more sig figs in one dimension than I do in the other. And if I were to do long multiplication, I would get a ton of question marks, wouldn't I? We're going to skip all of that because of time. And instead, we'll just go straight to the rule. Here's what multiplication does. When you do multiplication and division, you're going to count sig figs. How many sig figs does this first number have? They're all digits, so they all count. How about this one? They're all digits, they all count, there's just fewer of them. Your answer will have the fewer sig figs. So 2 is smaller than 6, so my answer when it's done must have 2 sig figs. So I'm going to punch this in the calculator, and I get this. I'm going to round it to 2 sig figs. I'm going to pick these two. So I'm going to round to the ones place, and this is the answer. Multiplication and division care about sig figs. Notice I wrote something different there. Multiplication and division care about sig figs. Addition and subtraction care about places. They are different rules. Do not mix them up. You will get the wrong answer. Okay, so you are learning 2 algorithms here. Very, very critical because a lot of students want you to just say, oh, this is the easier rule. I'm going to apply it to everything. And then everything falls apart. Now, for real systems, we're not dealing with estimations. I am not putting 70,000 gallons of fuel on the Saturn V. What you are putting... So you are not putting this many gallons on the Saturn V. You are putting this many gallons on the Saturn V. One of the numbers had 1 sig fig. The other one has 9. So in rocketry, the number of sig figs is an enormous number because it has to be. So if you need to know something precisely, you cannot estimate it to 1 sig fig. You have to measure it further than that. Oops, I'm just going to go to the next slide anyway, so we'll just put this up here. So for instance, if I was doing this math problem, this would be insufficient for something that required precision work. Because I have a number that's very precise with 5 sig figs, and I have a crappy number that's been measured with only 2 sig figs. That second number is not reliable at all. As a result, the precision of my answer is going to be affected. So here's what we're going to do for these calculations. And I am sort of choosing extremes here, just to show you how this works. How many sig figs are in each number? This one has 5, and this one has 2. When I multiply these together, my answer should have whichever is fewer, 5 or 2. That's this. So when I punch this in the calculator, which is right here, 5.4336 times 1.2, this is the answer I get, 6.52032. And I'm only allowed to have 2 sig figs, because that's what we decided, based on the rules. So I write this as my answer. Oops, there you go. All right. How about this one? I'm going to have you try this. I want you to report the correct answer to the correct number of sig figs using the multiplication and division rules. So type your answer in the chat once you got it. All right, let's see what we get here. So I'm going to punch this in the calculator on the screen. 34.836, 0.380, divide. And I get this long number, 91.6736. How many sig figs do I actually get to report? So this number has 5 sig figs. This number has 3 sig figs. I get to keep the smaller of the 2 sig figs. So that would be 3. So I would report 91.7. And that's our answer. Very good. Everybody got it right. All right. How about this one? Tell me the answer in the chat. Yeah, to answer your question, Kate, so we don't just truncate numbers, we do it to round to that last spot. And everybody got the right answer. And if you feel dirty when you type that in, you're like, 4, that's so imprecise. Ugh. Then that's the correct response, right? Because you have this very, 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 very precise number with 6 sig figs, and then you have this one, which is just 1 sig fig. I like to call this the cake analogy. If you make a cake with great ingredients, and then for the eggs you use rotten eggs that have been sitting out on the counter for 4 days, you're going to have a shitty cake, right? Because despite the quality of all the other ingredients, if you have one bad ingredient, you ruin the recipe. Multiplication and division operate on that principle. If you have one value that destroys the precision, everything else is thrown into suspect. Baking is chemistry. Baking is applied chemistry. Well, not just baking, but cooking in general. When we get to organic chemistry, I talk a lot about cooking because there's a lot of different things that you can do in cooking, and their basis is in biochemistry. Like, why do I do this thing? Why do I cook this at this temperature for this long? Oh, you're denaturing the proteins. It makes them more solid. This is why eggs solidify when you heat them as opposed to everything else, which tends to liquefy. All right. Last thing I'll say today before we go, because we're out of time, if you're using your calculator and you type in numbers, let's do this example on screen. I'm going to type in, so clear everything, 6.362, 1.638. Look what the calculator does. Boop. But if I write these numbers vertically, and I'm adding them, I get this, and if I do sig figs, this position is known, so I get to keep everything. What's the correct answer? And the answer is not what your calculator tells you. Your calculator does not know what sig figs are. So if it doesn't know what sig figs are, and it sees zeros afterward, it's going to truncate them because it thinks they are unimportant. That is because your calculator is stupid. So be very careful. Always follow the sig fig rules and do not trust your calculator to show you the correct answer because it does not know what sig figs are. Your calculator is operating on the premise of, I only care about the value, but we're scientists, we care about the precision. This is important because if you send something to the laboratory and say, I need to administer 1 milliliter of medication to my patient. Oh, so the answer to this one would be 8.000. But if you say to the lab, I need this medication, and they're going to say, oh, okay, there's 1 sig fig, so any number between this and this satisfies this. In reality, you needed to give them this much, which means that any number between... Oops, that's too much. Sorry. So, any number between this range would satisfy this. If the lab sent you back this amount for this, you have overdosed your patient by 40%. That could be fatal, right? If you are giving something to, like, I don't know, like a puppy or a baby for pediatrics, and you can only administer 1 milliliter of medication, and you give them 1.4, you've given them 40% too much medication because you didn't write down enough sig figs. That could be fatal, and you would be sued for malpractice. So sig figs are extremely important because we need to know the precision of the tool so that when I go upstairs, because I understand sig figs, if you need 1 milliliter, I'm going to roughly give you 1 milliliter. If I got 1.3, it rounds to 1. That's close enough. But if you need 1.00, I know, oh, I need to use a much better tool for this. You need more precision. And that could be very crucial. Okay, so don't overdose the patient. Make sure you are following the rules for sig figs. So this is relevant in medicine, believe it or not. All right, when we come back, what we're going to do on Thursday is we're going to do combined my goodness. We're going to do combined operations. So what do you do if you have to add and multiply at the same time? Stuff like that. And then we'll round it off with doing some dimensional analysis, which is going to be the meat and potatoes of the conversions that we do in this class. So I do want to thank everybody for showing up to the lecture. This is probably the worst part of the class, Chapter 2 and then Chapter 6, because it's so much math. But make sure you're working on the practice problems and hang in there, because it gets better. Chapters 3 and 4... not super easy, but they are relatively simpler in terms of content. All right. That's all I got. Make sure you do the quiz for chapter number 1. It's due on Thursday. Closes on Friday. We'll talk about lab number 1 next time. Take care.